Hey guys, this is the first part of the formal languages. Let's see what we got for today. Let me first review the big picture of the course that I gave you in the first day. You remember we said the foundation of computer science is called the theory of computation, which is this course. Actually, this course is a taste of that. So this theory is divided into four branches: formal languages, automata theory, computability, and complexity. And you remember we said the four three from the bottom gives us an idea what can be done by computer, what kind of problem we can solve by computer. And the third one, the complexity theory, gives us an idea that which kind of problem are tangible or practical. You can solve a problem and it takes centuries. So, theoretically, it is computable, but it is not a, feasible problem to be solved by computer. We start from the bottom one, the formal languages. The objective of this lecture will be formal languages. But formal language actually it's a language, and every language consists of sentences or string. We can call it string as well. Actually, in this course, mostly I will call it string instead of sentence. But if you read other books or articles, they might call it sentences as well. And every string or sentence needs some alphabet. So first we start with the alphabet. Okay. Just keep in your mind that all of these stuff that we are talking about would need a mathematical model behind them. All right. So when we say a string is a mathematical object. Anything I mention here is a mathematical object. Okay. First, we start with this alphabet, and then we define strings, and then we will define some operations on strings that you guys are familiar with majority of them, but to be on the same page, I have to mention them from mathematical point of view. When we finish this, then we will define formally the formal languages. Let's start with the alphabet. What is alphabet? Alphabet is a non-empty and finite set of symbols. So it should be non-empty, it should be finite, and it consists of symbols. All right. Is there anything in this definition that we have not defined before? We know the non-empty, we know finite and infinite. And what is symbols? We don't have any term simpler than symbols to define that. So we can assume that everybody understands this. So in other words, the symbol here is considered as the primitive data, primitive. So we don't need to define it. All right. Okay, so this is the alphabet. Pay attention, please, that it should be finite. We don't have an infinite set of symbols. It's not a practical thing. And if it is empty, again, it is not a practical thing. We cannot make a language with an empty alphabet. We should have something. So we denote the alphabet set with sigma. So always sigma is the alphabet, right? And we assume that the symbols should be indivisible, right? So for example, BH, if you say, okay, I want to use BH as a symbol, it's not a symbol, it's two symbols. It should be indivisible. Let me take some examples. A, B. These are some alphabet. 0 and 1, another one. Epsilon, alpha, and beta. The other thing that you need to know in this slide is this guy is our celebrity alphabet. What does it mean? It means that we use this alphabet a lot in this course. So I usually use this cool guy for our celebrity things. So alphabet is done here. Let me give you some notes. So usually we use lowercase letters, English lower letters. You see, so like A, B, C, something like that for alphabet. Sometimes we use numbers like this 0 and 1, but majority of time, as I said, we will be using this kind of symbols. Let me ask a question. Is this a suitable thing for being alphabet? We know that this is gamma, it's a Greek symbol, and this is a Farsi or Persian character. It's equivalent to P. And absolutely, I have no idea what these two are. I just copied and paste to make it a little bit scary. I don't know. So if as long as it is indivisible, then it can be a part of the alphabet. Okay, so we are done with the alphabet. Let's turn to the string. A string is a finite sequence of symbols. Pay attention to this finite. It's very important. In computer science, we don't have infinite size string. So it should be finite sequence of the symbols. Yeah, as in computer we have limited resources, so infinite sequence of symbols will be impractical. So no infinite string up to this point. Let me take an example. Let's say this is our alphabet. Usually our alphabet is not that much big, but here just as an example. Here is a valid string, cat, C-A-T, we have dog, D-O-G, we have apple, A-P-P-L. Yeah, so all of them are valid. Another example, we have our celebrity alphabet A and B. Question is, are the following strings valid? Okay, B-A-B-A. Any objection? AABB. Okay, so overall, do you have any objection on this? All of them are valid? You could object about this. What is this? This is not a valid string over this alphabet. Not all of them are valid because this dot 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 is not a valid string because dot is not part of the alphabet. All right? Okay. Another thing I want to ask is these B A B A B B and blah blah, whatever it is, they are meaningless. Do you think they are valid strings? In the definition of the string, I didn't talk anything about the meaning, right? We just said it is a finite sequence of the symbols of alphabet, right? There is nothing about the meaning. So most of the things that we will see in this course looks like this. Because it's a math course, yeah? In math, we don't care about the meaning at all. We will see more about this thing that I just stated. What is a string variable? So you guys are familiar with the concept of variable. Variable is let's say it's a name, or here we usually use the lowercase letter, let's say W, U, or V, and we call them string variables. So we can assign a string to these guys. In some cases, if we need more variable, we might use X, Y, Z, and something else, but majority of time we will be using this string. Here is some examples. For example, W is a variable. We can assign some strings to them, something like this. Okay. The size of this string. The size of the string, you can guess that is the number of symbols, right? So if the string, we call that string W, then the number of its symbols will be its size, and we denote that with these two vertical bars. Here is some simple examples. AAA is the size is 3, 5, 4, right? I am sure you won't confuse between this size and the set size, right? These are two totally different things. So the string is a sequence of things. It looks like a list, right? So the repeated thing, we don't care about the repeated thing. Yeah? So in general, we would say the size of this string, which consists of n symbols, equal to n. So what is empty string? Empty string, as you can guess, is a string without any symbol, with no symbol, or in other words, a sequence of zero symbols. And we need a notation for that in this course. Please pay attention that don't confuse between this. We in high level languages we use these empty double quotes, or in some other languages single quote as the empty string, but in this course we don't have this, so we need a notation for that, and we used lambda for that. So lambda is empty string in this course. So what is the size of the lambda? Yeah, definitely 0. Okay. Some authors, especially very old ones, they like to represent empty string with epsilon. But the modern books, and here in this course, we will be using the lambda. And based on the knowledge that we got so far, this lambda cannot be part of an alphabet, so it's prohibited, right? It is specifically chosen for the empty string. It cannot be part of the alphabet. We are done with the string. Now let's turn to the operations on strings. So first operation is called concatenation. This is something that you definitely know about that. Here we just define it from mathematical point of view. If we have two strings, u and v, so these are the variables containing some string, then the concatenation will be uv. And I'm sure you know that uv is not equal to vu, because the order matters, right? All right, so let me take an example. For example, if U is AA, BA, and V is BB, then you concatenate them, we get this guy. The length of the concatenation will be the addition of the each string. And another point here is the neutral element of lambda. So lambda is empty string. If you concatenate it with anything like this or this from left or right, it's neutral element. Here is an example. You see, you put lambda anywhere, it doesn't matter. It can be eliminated. Just remember that this is not empty string in this course. Okay, reverse of a string. Reverse of a string is we just need to write the symbols, the sequence of the symbols reversely. We just change the order, right? And we denote that with W to the R, that we pronounce it W reverse. If W is A1, A2 up to AN, then W reverse will be the reverse order. And here is very simple question. AABA, what is the W reverse? It will be ABAA. And this is a side note just for your information. You know the palindrome. Um, it's a string that if you read it from left or right, they are the same word or the same string. For example, radar, reviver, rotator, something like that. I collected some funny palindromes here. You need to ignore the spaces, apostrophes, and commas. Madam, I am Adam. A step not on pets. No lemons, no melon. Denise and Edna sinned. A man, a plan, a canal, Panama. I have an exercise for you guys here. You are gonna prove that if we have a concatenated UV and then reverse that, it is equivalent to reverse of the second one and the reverse of the first one, and then concatenated them. You need to say, okay, U is, for example, equal to U1, U2, blah, blah, U, let's say N, and you can put the V as V1, V2, let's say Vm, and then substitute these two inside here and try to simplify that. You will get here. Yeah, it's so easy. So what is substring? Substring is the same thing that you already know from the high level languages. Here we just define mathematically. So substring, any string of consecutive symbols of a string like W, any string of consecutive symbols, right? Any part of this string can be considered as a substring. Here is some examples. For this AA, from the beginning it is a substring, or AB can be a substring, or BABA, these three can be a substring, and so forth. You can continue here. So this guy maybe is interesting. So lambda can be a substring of the any string. And why is that? Because we said W lambda is equal to W. So if we put lambda here, or we can put lambda here, so lambda is a substring of any string here. And also we can consider the whole string as a substring as well. Prefix and suffix. If we can separate a string into two parts, for example, if we have W and we can separate two parts like UV, and then we would say U is a prefix and V is the suffix. Let me take an example to clarify that. W, for example, is this. If we pick AA as the prefix, then the rest of that will be suffix. Could we pick other things? Of course we could. So in the next slide, I collected all of the possible prefix and suffix of the same string. So lambda is a prefix for here. Then the rest of that, which is the whole string, will be suffix. And you can figure it out. So if A is prefix, the rest of that will be suffix, and up to this point. So this is the prefix and this is the suffix. And if we pick the whole string as a prefix, then the suffix will be lambda. So lambda is something that can be prefix and suffix, but of course not at the same time, right? And the reason is, again, this equation we have. Exponential operator, it looks like the elementary algebra. We have a string, we denote it, let's say, with W. And if we concatenate it n times, which n is a natural number, of course, then we will get W to the n. So W to the n is a concatenation of n copies of W, like this. And we denote that with W to the n. You see, it looks like an elementary algebra. And concatenation looks like a multiplication, right? Okay, so here is some simple examples. If W is just A, let's say our sigma is A comma B. Let's say it could be something else. It could be even just A, but let's say it is the alphabet is A and B. So what is W square and what W cube? Just concatenate this A twice. It will be A square. Pay attention that this is a string, not a number. It's not elementary algebra. And A cube looks like this. Let me take a little bit more interesting string. So if the string is A, then what is W square? Just concatenate A, something like that, right? And you can keep the string like this, or you can combine these two as A square, right? And here again, A square, something like that. So A square BA cube. Oh yeah, we have 3A here. And if we ask concatenate another one, and we get this. And in general, we would say if we concatenate W to W to the N from left or right, because they are equivalent, the same W, we will get W to the N plus 1. And n is a natural number as usual. All right, let me take an example for the size of the string. Let's say W is equal to A to the M, B to the M, and M is a constant, of course, a natural number. What is the size of the W? So this W is A to the M, B to the M. What is the size of this? Yeah. So because we have m copies of A here, m copies of A, m copies of B here, so it will be m plus m. Yeah. Okay. Now let's turn to some interesting things. So we have some special cases. What is W to the 0? So W is a string. Remember that. And with the knowledge we got so far, what is W to the 0? We know W square, it means WW. And we know W to the N is N copy of W, right? The question is, what is W to the 0? That's lambda. But I'm going to ask you to prove that. Mathematically, you should be able to prove that. Yeah, try to prove why W to the 0 is equal to lambda. It is the source of confusion, I know that, because your mind is set based on the algebra, I know that. So W to the 0 is not equal to 0 or even 1 or whatever. Because, W, this is a general rule. When we have W, what is W? Is it a string, right? Any operation on a string will give you a string. This is a general rule. If you keep this in your mind, it will prevent the future issues and confusions. Another example, I want to give you is this AABA to the 0. We said it is equal to lambda. Why we said that? Because this is a correct statement. If W to the 0 is lambda, did we say anything about W? W can be anything, right? It can be any string. So if you substitute any string here, you will get lambda. But you should pay attention that the whole string should be to the 0, right? For example, if we remove that parenthesis, we will get something like this, A to the 0. Then this 0 belongs to only just A. And this A to the 0 will be lambda. So what we get, B lambda, which is equal to A only B. So pay attention to difference between this and this. Now let's turn to the formal languages. But we still need to define two other operations. So we need two new operations. After I define them, then you will be ready to understand the definition of formal language. The first one is a star operator. And a star operator, we apply it on the alphabet. What is the definition of that? If the alphabet is sigma, we define sigma star. So this star is an operator. Sigma star is the set of all possible strings that you can by concatenating 0 or more symbols from the sigma. What did I say? All possible strings that you can make by the symbols of the alphabet. Let me take an example first, and then I return back to review this concept again. Let's start with a very simple example. Let's say sigma is just A. What is sigma star? Now return back to this definition. All possible strings that we can make by concatenating 0 or more symbols from the. So what is sigma star here? All possible strings that you can make with A. What are they? The first one is lambda. These, and it's infinite. Do you agree that? It's infinite. Because all possible strings, we can concatenate, one more, one more, one more, one more, and we can, it's. If you are confusing that why it is infinite, yeah, just remember that just this alphabet cannot be infinite, and also the string size cannot be infinite, right? But this set can be infinite because when you concatenate, let's say n times, then the next one will be n plus 1. So you can create another string, another string, another string, yeah? So sigma star is an infinite set. Let me take another interesting example. This time we will have our celebrity alphabet A, comma B. Now the question is, what is sigma star? Recall the definition of the sigma star. All possible strings that we can make by concatenating 0 or more of these symbols. Okay, so 0 concatenation always give you the lambda. 1 concatenation give you A, B. 2 concatenation, this is getting interesting. 2 concatenations give you AA, AB, BA, BB. So you see all possible strings again, again, again. So up to this point, two concatenation. Up to this point, one concatenation. In zero concatenation. Now we need to three concatenation. So how many string you can create with this A and B? A, let's say B, A, B, A, B, A, and so forth, yeah? So the important point here is that you understand that sigma star contains all possible strings that can be made by the symbols of an alphabet. But you just pay attention to that zero or more concatenation. Okay, so you remember what strategy we picked? The strategy we picked to enumerate all of these combinations, something like that. If you want more fun, yeah, just go ahead and create a sigma star for A, B, C and see what would happen. This is your exercise. This was the first operator I wanted to mention before defining the formal languages. Another one we have, it's called plus operator. So plus operator is very similar to the star operator, and their definition, the only difference is this guy. In the sigma star, you had zero or more concatenation. Here we have one or more. So if we remove the zero, what we are missing here? Only lambda. If you enumerate this sigma plus here, you will get something like that. You see, just lambda is missing here. So A plus or sigma plus is equivalent to this. Again, the sigma plus is an infinite set. Okay, and we miss the lambda. It does not contain lambda because it starts with one concatenation. The example of our celebrity alphabet is the same strategy, same thing, just we remove the lambda. Okay, so based on this knowledge that you just got, what is the relationship between the sigma star and sigma plus? So you remember that this guy is a set and this guy is a set. Both of them are sets. So whatever you learn about the sets is applicable here. Okay, so what is the relationship between these two? So this guy, if you add a lambda here, if you add a lambda here, you will get sigma star. But add, we don't have in the sets. Yeah, we should use the union. Yeah, if you union the lambda, and we will get the sigma star. And also on the other side, if we remove the lambda by minus from the sigma star, we will get sigma plus. You might asking this question that just for a lambda, removing a lambda, we created a new operator plus? Yeah, we did that. We will see later that some machines that we will introduce later, they don't like lambda. That's why we removed that. I think we are ready to define the formal languages. Let's say that sigma is the alphabet. And when we have the sigma, we can create sigma star. And you remember sigma star is all possible strings that you can create with the symbols of the sigma, right? All right. Now we would say any subset of sigma star is called a formal language. And since sigma star is a set that contains all possible strings, can we consider it as a universal set for all languages that we can create over this alphabet? Yeah, we can do that. It is a universal set for all languages that we can create with this alphabet. Let me take an example and maybe it make it more clear. We have our celebrity alphabet. What is sigma star? We know that. This is the sigma star. And we can pick some subset of this sigma star and they are a formal language. For example, L index 1, this is a subset of this guy and it is a formal language because L1 is subset of sigma star. How about L2? Yeah, as long as it contains A and B, any any string that contains A and B, you are sure that that string belongs to the sigma star. So any subset like this is a formal language over that alphabet. When we define a formal language, we should say over what? Well, we should specify the alphabet, okay? So yeah, L2 is a subset of L sigma star. That's why it is a formal language. How about this one? A to the n greater than or equal to 0. Yeah, I said here because this is a subset of that, but are we sure about this? Let's see. So, do you understand what language is this? This language is saying what? Its pattern is a to the n, and n can go from 0, 1, 2, 3, and so it's a set builder, right? So if you enumerate this, what you get? If n is equal to 0, what you get here? Lambda, yeah. If n is equal to 1, you get a, and then a, and a, and blah, blah, blah. Yeah, so this is this language, right? Is this a subset of sigma star? Yeah, of course it is. Sigma star contains all possible strings with A and B. Yeah, so definitely A alone, all of the strings that can be made by A alone is part of the sigma star as well, right? For example, this guy, you see, A. We have A here, see? A here, yeah? And you guess that if you continue, so A to the 4, A to the 5, and all of them, is here, right? So index 3 is a formal language because L3 is a subset of sigma star. So we already did that. So we represent it with the raster method. Now the interesting thing is some special cases. How about this guy? Is L4 a formal language? So phi is an empty set, right? It's an empty set. An empty set is a subset of all sets. Based on the definition of the formal language, we said all subsets of sigma star are formal language. And based on that definition, we would say yes, phi is a formal language. This is another useful language, and this is, formal language as well, because both, this guy is subset of the sigma star, right? So lambda is subset of the sigma star. So these two guys are two special formal languages, and we have two names for them. So empty language, this guy or phi, and lambda language, this guy. Okay, we will see later that why we introduce these two guys. So from now on, when I say language, I mean formal language. And also pay attention that formal language is a set. Set of what? Set of strings, right? So since it is set, it have all of the properties we mentioned for the sets, all properties. And the third note is pay attention that this guy we just mentioned is a language, right? So it is a set, but this guy alone is a string, is an empty string. Sometimes students make a mistake between these two. If you understand the nature of each one, then you won't get confused at all. So this is a string, this is a set, and language, two different things. Okay. And the fourth note I want to mention here, some authors, as I said, prefer to use the sentence as a string. Yeah, we prefer, actually I use both of them, but majority of time I will be using the string, not sentence. Sets can be finite and infinite, and since languages, formal languages, are sets, they can be finite and infinite as well. So this is our first categorization of the languages. So formal language can be finite or it can be infinite. So if this is the all possible formal languages in the world, right? We can divide them between two. So infinite formal languages, finite formal languages, all right? We will see, several categorization in the future. This is one of our very interesting and desired thing, that to categorize the languages from different point of views. So here we categorize them uh, from the size point of view, and you will see later many other things. Okay, so I put some exercises here. So I will give you some languages like this, and I ask you to enumerate that. Just, 5, 6 strings is enough. And between the languages that you will see in the future, this guy is our celebrity language. We will see this a lot.